So our first problem says here, two charges 10 microcoulomb and minus 10 microcoulomb are placed at a point A and B, separated by a distance of 10 centimeters. So let's draw here. Here we have 10 microcoulomb and here we have minus 10 microcoulomb. Both are separated by distance. Let's say this is point A, this is point B, and both are separated here by a distance of 10 centimeters. So this gap, let's assume this is 10 centimeter. Great. Find the electric field at a point P on the perpendicular bisector of AB. Perpendicular bisector means equatorial plane. So perpendicular bisector, here let's take a point P and let's assume that this is perpendicular and it is bisecting. Bisecting means this will be 5 centimeter and this will be also 5 centimeter. Great. So we have to find electric field, okay, and this P point is at a distance of 12 centimeter as per the question. Okay. So AB at a distance of 12 centimeter from its midpoint, right? We have to find the electric field. So if you remember, electric field due to a positive charge is radially outward, right? And electric field due to a negative charge radially inward. So let's draw here electric field due to the charge at A, which is 10 microcoulomb, will be radially outward along the line joining the charge and the point P. So let me draw here. An electric field at point P due to the negative charge B will be along the line joining. So it will be in this direction. Correct? Great. So this is our electric field EA and this is our EB. Now we have two vectors. One is EA in this direction, right? And we have EB in this direction. Where will be the resultant? We know from 11th standard, if we have two vectors like this, then the resultant of such a pair of vector will be along this line, and this will be our net electric field. Now we can figure out this by using components. So we can find the component of EA. What will be EA component? It will be EA cos theta here, and EB, that also EB, where theta will be this angle. We have to figure out this angle. So we will find this angle, and here also it is theta. So what will be EB? It will be EB cos theta in this direction. Correct? What will be the component of EA in this direction? It will be EA sin theta, and here it will be EB sin theta. I hope this is clear. Okay, so let's solve this using component wise. First of all, let's figure out our E net. Okay, so E net here will be EA cos theta plus EB sin theta. And what will be, this is along x-axis. What will be our net electric field along y-axis? So E net, I am writing here along y-axis, that will be, y will be EA sin theta upward, you can see, while EB sin theta is downward, so it will be minus EB sin theta. Let me make some changes here. It is cos theta, EB cos theta, my mistake. Okay, great. So we have electric field E net, okay, along x-axis is both cos theta, and along y-axis EA sin theta minus EB sin theta. Let's figure out what is EA, EB cos theta sin theta, correct? So first of all, let's figure out what is EA. EA, electric field due to the charge at A, will be K. K is 9 into 10 to the power 9. Charge Q, which is present at A, whole divided by, what's the separation? AP square. And electric field at B, electric field due to B will be K Q B upon BP square. Correct? Now what is our AP and BP? Let's figure it out now. So AP and BP, if you look at the triangle, let's make it as O. Okay, so from the triangle AOP, if you use Pythagoras theorem, AP square will be equals to how much? It will be PO square plus AO square. And you can see this is a trio. This is 5 centimeter AO. PO is 12 centimeter. So AP will be 13 centimeter. You can solve using Pythagoras theorem. You will get this 13 centimeter. If this is 5, 5 square is 25, 12 square is 144, and when you add both of them, you will get 169, whose root is 13. So AP we got as 13. Let's substitute here. So this will be 9 into 10 to the power 9. Charge at A is 10 microcoulomb. 10 into 10 to the power minus 6. Micro is 10 to the power minus 6 whole divided by AP. AP is 13 centimeter. So 13 into 13, and centimeter is so 10 to the power minus 4. It will convert into meter. Similarly, if you put the values here, K is again 9 into 10 to the power 9. Charge at B will be, our charge at B is 10. So 10 into 10 to the power minus 6. Let me remind you once again, we don't take the negative sign. Since it is negative, our direction of arrow is downward. If it was positive, the arrow will be different. So we have already considered the negative sign in the arrow, right? Whole divided by, what is BP? Again, if you take the triangle POB, BP is nothing but 13. You will get 13. So 13 into 13 into 10 to the power minus 4. Correct? Now look at EA and EB. Magnitude wise, EA is equals to EB. So if EA is equals to EB, what will be the net field along y-axis? It will be 0. Why 0? Because of this negative sign, both are cancelling out. Correct? EA and EB got negative. While in case of x-axis, if you look at this first equation over here, okay, what can we find? That the electric field adds up. So what we will do, let me scroll up and let's find the net electric field along x-axis. So net electric field along x-axis will be EA cos theta plus EA cos theta, because EB and EA both are same, so EA cos theta. Now let's make it as 2 EA cos theta, because 1 apple plus 1 apple, 2 apples. EA cos theta, take it as apple. Now this becomes 2 into, what is EA? EA is nothing but 9 into 10 to the power 9 into 10 into 10 to the power minus 6 whole divided by, let me scroll a little, 13 into 13, 169 into 10 to the power minus 4. What about cos theta? Let's go back to our triangle. So cos theta here will be angle theta, this one. Why? Because we have assumed this angle as theta. So these are corresponding angles. So if this is theta, this is also theta. Why? Because angle opposite to equal sides are equal. So even this is theta, alternate angle, right? So that you can justify from this diagram as well. So these two theta will be base upon hypotenuse, right? So cos theta will be base. What is base? Base is AO upon hypotenuse, which is AP. What is AO? 5 centimeter and AP 13. So let's substitute this value of cos theta over here and find our final result. So our final result will be here 2 9s are 18 upon 169 into, let's simplify the powers, 10 to the power 9 and 10 minus 6 is 4, 10 to the power 4, and this 10 to the power 4 goes up, so it will make it 10 to the power 8. Let's keep it 4 for the time being. And what is cos theta here? Let's substitute cos theta as 5 by 13. So let's make it here as 5 by 13. So this will give us 18 into 5, which is equals to 90 upon 169 into 13. 169 into 13 will give us 2197 into 10 to the power 8. Now if I divide 90 with 2197, let's see how much we get. So we get nearly 40, 0 point actually we will get, but we will take the powers and make it as 4 into 4.1 into 10 to the power 6. And what's the unit of electric field? Unit of electric field is newtons per coulomb. So this is our result for the first question. Okay, I hope this is clear. Let's move to question number 2. Question number 2. It says a ring of radius A. There is a ring with radius A contains a charge Q distributed uniformly over its length. Okay, fine. Find the electric field at a point on the axis of the ring at a distance of x from the center. So let me make here a perfect circle. So let's imagine this circle here. Okay. So this is our ring, and this ring, okay, due to this ring we have to find electric field. Where we have to find electric field? Okay, along the axis. Okay. So this is our any point at a distance of x from the center. Okay. And from this point, let me make a straight line here, our radii. Okay, so this is our radii. Wait a minute, let me make it straight. Okay, okay, here it is. Okay, so this is our any distance A. Okay, so this is our ring, and the blue region is hole filled with charges. Okay, let's take O as a center. Let's say this is the point A where it is meeting, and let's imagine a very small part of charge here, dq. Dq is what? A small part of charge, infinitesimal charge here. We will integrate this charge to get the total charge which is all over the ring, correct? And due to the small piece of charge, at any point P, the field will be what? The field will be radially outward, right? So let's join this point, joining this charge, small charge, and point P, and at this point the field will be radially outward. But this field, since the charge is dq, the field will be also dE. Okay, it won't be total electric field, right? We will integrate this dq to get the total field at point P. Okay, now let's draw this straight line here. Let's finish it. So this, if we assume angle theta, what will be the component of dE along this side? It will be dE cos theta. If this is our electric field dE, then component of dE along this side will be dE cos theta. Sir, why you are considering dE cos theta and not dE sin theta? Be very careful. Very important concept it is. dE cos theta lies in this direction, then dE sin theta will lie in this direction as usual. Correct? But as we have seen in the previous problems also, if dE sin theta goes down, and if we imagine a small piece of charge over here, and we try to figure out our field in this direction, then because of that, the component of electric field along sin theta will be upward. These two components will cancel out each other. That's why we don't consider sin theta. Okay, we only consider cos theta, because all the cos thetas will add up, while all the sin theta will cancel out because of opposite in directions. Cos theta will be along the axis, while sin theta will be normal or perpendicular to it. I hope this is clear. So what will be the field due to this infinitesimal charge? So that will be dE, that is equals to dq kq. K is what? 4 pi epsilon naught q, and what's the charge distance? AP square, right? From that point A to point P square, AP square. Great. Now this is dE, but our net electric field is what? That is along x-axis. So dE cos theta. So dE cos theta, okay, that will be equal to how much? dE cos theta will be equals to dq upon 4 pi epsilon naught AP square and cos of angle theta. Correct it is. Now what's cos theta here? If this is theta, this will be also theta. Correct? Vertically opposite angles. And if that is theta, then what is cos theta? Cos theta is base upon hypotenuse. So let's put here, what is our base? OP upon hypotenuse, AP. Great. Now let's figure out what is our AP over here. So if you use the triangle AOP, AP square will be equals to OA square plus OP square. So OA is A, OP is X, that is our AP square. Great. And what will be our AP? Root under A square plus X square. Let's substitute here these values. Okay. So this will give us the total electric field. Okay. That will be E, which is equals to integration of dE cos theta. We have to find it due to all the charges, not only due to dq. So dE cos theta, and this dE cos theta will be equals to integration of dq upon 4 pi epsilon naught AP square and AP, that will be AP cube. So let's find it here, root under A square plus X square, that is AP whole cube into OP. Correct? And what's OP? Look at the diagram. OP is X, so into X. I hope this is clear. Now let's take the common out constants. Let's take the constant out of the integral. What are the constants? What are the values which will not change? Okay, that is X upon 4 pi epsilon naught, and this root and that thing I am writing it as A square plus X square whole power half. Root is half and whole cube. To make it simple, that is also taken out, and integration of dq. Correct? Now integration of dq will give us nothing but the charge, the total charge, because integral gives you the total sum. So this will be q whole divided by 4 pi epsilon naught, and this half and 3, that will become a square plus x square whole power 3 by 2 due to a ring, okay, which contains charge and positive charge. Similar way you can think of negative charge also radially inward. So this is our electric field due to a ring of charge. Question 3 says 3 particles each having a charge of 10 microcoulomb are placed at the vertices of an equilateral triangle 10 cm. Find the work done by a person in pulling them apart to infinite separation. See, if 2 things are joined together, or 3 things are joined together, or 4 things are joined together, they are joined together because of some force, right? Or the work you have done on that, right? So the amount of work we require to put them together will be always equal to the amount of work done to separate them, right? Okay. So here, because forces here, electrostatic force is a conservative force, right? So hence the work done to pull them apart will be equal to the amount of work done in putting them together. So let's figure out what is the potential energy. So if there are 3 particles each of 10 microcoulomb, let's put the first charge over here, okay? And first charge, when you put here, what will be the potential energy? 0, right? When you place the first charge, u1 will be 0 because there is no charge to influence it, right? If you place the second charge over here, this is 10 microcoulomb, so let me write here 10 into 10 to the power minus 6, correct? When you put the second charge at this point, okay, at a 10 centimeter from the first charge, so this is 10, the second charge will be getting influenced by it. So u2 will be equals to how much? This will be 10 into 10 to the power minus 6, correct? At a 10, okay, sorry, that's a charge. So this is k, k is 4 pi epsilon naught, 1 by 4 pi epsilon naught, k, q1, q2 is 10 to the power minus 6 whole divided by separation, which is 10 centimeter, correct? Let me repeat again. So the amount of work done in placing the second charge will be k, q1, q2 by r, okay? So k is 1 by 4 pi epsilon naught, okay, which we will put 9 into 10 to the power 9, okay, and q1, q2 by r. Now when I place the third charge at this point, let's say, okay, at a distance of 10 centimeter from the first charge and at a distance of 10 centimeter from the second charge, okay, so this will be again 10 into 10 to the power minus 6. Amount of work done will be u3, and this u3 will be this charge influencing the first and the second, right? So that will be k. I am just putting 1 by 4 pi epsilon naught as k, and into 10 to the power minus 6 q1, q2, q3 upon 10 upon r, which is 10 into 10 to the power minus 2, and the influence of the third charge with the second charge, that is plus k into 10 to the power minus 6 whole square. I am just making it whole divided by r. Okay, now someone can say, sir, you can't directly take u as 3 times. Yeah, you can take it, but here the condition is all the 3 charges are similar, right? Or they are placed on the equilateral triangle. What if you are placing them on a square? Then things will be not same. So be very careful, the separation will be changed, and in that case things will go wrong if you directly apply the formula, okay? So here we can write u will be equals to the sum of u1 plus u2 plus u3, which is 3 into 9 into 10 to the power 9, which is 3 into k into q1, q2. q1 is 10 into 10 to the power minus 6, all of them are same, so 10 into 10 to the power minus 6 whole divided by 10 into 10 to the power minus 2, correct? So when you simplify, 9 3s are 27 here you got, okay, and this 10 and 10 100 11 and 10 to the power minus 12, 10 to the power minus 1 whole divided by 10 to the power minus 1, so you left with 27 joules, okay? That's your answer for this particular problem. I hope this is clear. Question number 4. Question 4 says 2 charges 10 microcoulomb and 20 microcoulomb are placed at a separation of 2 cm. Find the potential due to the pair at the middle point of the line joining the two. Okay, very simple. you have two charges. One charge is here 10 microcoulombs. Another charge is here 20 microcoulombs. And both are separated by a distance of 2 centimeters. So this gap is 2 centimeters. And they are asking find the potential at any point P which is at 1 centimeter. Midpoint is 1 centimeter. Right? So let's call this as charge A, this as charge B. Potential at point P due to the charge A will be VA and due to B is VB. So VA plus VB we will get. Correct? And VA is how much potential? VA will be equals to the charge K into charge QA upon the separation AP. And potential due to B will be K into QB upon BP. So potential due to the first one, VA, will be equals to 9 into 10 to the power 9. What's the charge? 10 into 10 to the power minus 6 upon separation, 1 into 10 to the power minus 2. Potential due to B will be equals to 9 into 10 to the power 9. 20 microcoulombs, 20 into 10 to the power minus 6 whole divided by separation once again 1 into 10 to the power minus 2. Let's find the potential by adding both the values. So VP will be equals to VA plus VB. Adding both the values, let's take few parameters common, like 9 into 10 to the power 9 taking common, 10 to the power minus 6 taking common, and 1 upon 1 into 10 to the power minus 2. Here we left with 10 plus 20. Correct? So 10 to the power 9 and this 11 minus 6 goes here because 10 to the power minus 2 goes up, and 9 to 11 minus 6 is 5, right? So 9 into 10 to the power 5. And 10 plus 2 is 20 is 30. So this will be 9 3s are 27 into 10 to the power 6. And what's the unit of potential? Volt. Please write the units, very important. Let's move to, I hope this is clear, let's move to next question. Okay, so question 5 says 5 into 10 to the power minus 7 minus 2.5 into 10 to the power minus 7 and 1 into 10 to the power minus 7 are held fixed at the 3 corners of an equilateral triangle. So let's draw a triangle here first. Okay, so this is our triangle. Okay, and in this triangle, okay, equilateral triangle, let's assume one charge here is 5 into 10 to the power minus 7. Another charge is minus 2.5 into 10 to the power minus 7, and here 1 into 10 to the power minus 7. And what's the equilateral triangle side? Side 5 centimeters. So this is 5 centimeters. Fine. Find the electric force on the charge at C. Okay, so let's go in the same order as they are saying A, B, okay, and C. Correct? So A, B, and C. So at A, B is minus, B is minus 2.5 and C is this 1 into 10 to the power minus 7. Correct? We have to find what? Force. Now, if you are finding the force on C due to A and B, because they will only the one who will influence C, right? So electric field, force at C due to A will be attractive or repulsive? It will be repulsive, right? Because the charge at A is positive and charge at C is again positive. So they will repel each other. Along which direction? In this direction. Okay, let me redraw this to make it a little straight. So it will be along the line joining the A and C. So this will be force on C due to A. Okay. Now secondly, the force on C due to B, attractive or repulsive? It will be attractive. Why attractive? Because one is positive, one is negative. So they will be attracted along the line joining the two. So this will be force on C due to B. Correct? And if this is an equilateral triangle, what will be this angle? This angle will be 120 degree, right? Yeah. Why 120? Because this is 60 and that will be linear pair. Correct. So let's write now what is the force on C due to A. So force on C due to A, that will be equals to K. I'm just putting here K. Charge on C, that is 1 into 10 to the power minus 7. Charge on A, 5 into 10 to the power minus 7. Whole divided by the separation square. What's the separation? 5 centimeters. So 5 into 10 to the power minus 2 whole square. I hope this is clear. This is FCA. Now what is FCB? So force on C due to B, that will be equals to K, I'll put the value of K, into the charge on C, which is 1 into 10 to the power minus 7. The charge on B, which is minus, I am not taking the negative sign, again I am repeating. Why I am not taking the negative sign? Because we have already considered it in the arrows, right? So into 2.5 into 10 to the power minus 7. Okay, this is our Q1, Q2 upon R square. R is again 5 centimeters, so 5 into 10 to the power minus 2 whole square. And what's the theta here? 120 degree. If two vectors, force is a vector quantity? Yes. So how do we add them? Can we add them directly? No. We have to use a resultant formula. What is our resultant of two vectors? The resultant of two vectors is given by this relation, a square plus b square plus 2ab cos of angle theta. Correct? And cos 120 is minus half in case if you don't know. So let's substitute. Before we substitute, let's simplify this, okay? Because k is common here, okay? So I am just taking here, let's rewrite this expression because it will be lengthy. Let me write it on the little left hand side, okay? So here the net force on C will be equal to root under FCA, which is K, and let's simplify it here a little bit. 5 into 1 is 5 and 10 to the power minus 14. So 5 into 10 to the power minus 14, correct? Whole divided by 25 into 10 to the power minus 4, correct? So 1 by 5, K into 1 by 5 into 10 to the power minus 4 goes up, plus 4 minus 10. I hope this is clear. First parameter square. Let's move ahead. Second factor, let's simplify it further. So this will become K into this, there is a K also here, huh? Okay, so K here into 1 into 2.5, that's 2.5 upon 5 as a 25, okay? And 10 to the power, you will see minus 14 and this 4 minus 10, same you will get. So let's put it here, plus K into 2.5 upon 25, okay? And into power 10 to the power minus 10 whole square, right? I hope this is clear. Plus, okay, now this plus 2ab, this plus 2 will cancel out and will become minus. Why minus it will become? Because cos 120 degree. Cos 120 degree is what? Minus half. So that will cancel out this 2. Let me repeat here again. Cos theta. So cos 120 will be minus half. That minus half and this 2 will cancel and make it minus a into b. So a is what? Let's put it again. So minus a is k by k into 1 by 5 into 10 to the power minus 10 and multiplied with how much? K into 2.5 by 25 into 10 to the power minus 10. Correct? Okay, great. Let's take now common out. Okay, so if I take common out from here, K is here, K square is over here and K square is over here because this K and this K, right? So we can take K square common from all the factor. I am just keeping it inside the root only. K square from all of them, and 10 to the power minus 10 whole square is also common. So 10 to the power minus 10 whole square. These two things are common in all of them. Okay. Let's see what we left with. Here we left with 1 by 5 whole square. Here we left with plus 2.5 upon 25 whole square minus here K and minus this, they will be squared, and this we left with 1 by 5 from here and into this will be 2.5 upon 25. This we left with. These two we can take it out of the root. So K square will become K, which is 9 into 10 to the power 9, and 10 to the power minus 10 whole square will come out of the root and become 10 to the power minus 10, right? And here we left with root under 1 by this, 1 by 25 plus. Now if you remove this decimal, you will get 0 here down and you left with 1 by 10. So here it will be 1 by 100 minus this will be removed here and you left with 10 here. So minus 1 by 50. I hope this is clear. Okay, so this is the thing we left in root. Let's make it more simplified. 9 into 10 to the power minus 1 root under this, let's make it 100. 25 fours are 152. 5 minus 2, 3 by 100. So this will be 9 into 10 to the power minus 1 into root 3 by 10. Why? Because 3 by 100 is root 3 by 10. This will become 9 root 3 into 10 to the power minus 2. And what we are calculating? Force. So this is Newton. I hope this is clear. So the correct answer for this is 9 root 3 into 10 to the power minus 2. Our sixth question says, two particles A and B having charges 8 into 10 to the power minus 6 and minus 2 into 10 to the power minus 6 respectively are held fixed with a separation of 20 centimeter. Okay, where should a third charged particle be placed so that it does not experience any electric force? Okay, so let me draw a rough diagram. So here we will put our first charge at any point A, let's say. Okay, and this is another one at B. Okay, and the separation between A and B is how much given here? 20 centimeter. Okay, we have to place the third charge. Let's place it here somewhere at C. Okay, at a distance of x centimeter from B. Clear it is? So separation between A and B is 20 centimeter and separation between B and C is x centimeter. Clear? All of them are in centimeters. Okay, now at A we have the first charge, which is how much? 8 into 10 to the power minus 6 coulomb. Okay, and at B we have second charge, which is minus 2 into 10 to the power minus 6 coulomb. Clear? Now they are saying, where should we place the third charge? Okay, the charge which is to be placed at point C, so that the net force is 0. Clear? Now first thing, to get the net force to be 0, okay, the resultant at force at C, okay, will be 0. Clear it is? So here let's figure out our force due to A on C. So force on due to A on C will be, force on C due to A will be equals to K, which is 9 into 10 to the power 9, okay, into the first charge, which is 8 into 10 to the power minus 6, okay, and let's assume the charge which is to be placed at C is Q. So capital Q, I am placing here capital Q, okay, whole divided by, what's the gap between A and C? The gap will be 20 plus x into 10 to the power minus 2. Correct? Equation number 1. So we placed our charge at C, which is at a distance of x. Now let's figure out the force on C due to B. That will be equal to 9 into 10 to the power 9 into, what is our charge at B? 2 into 10 to the power minus 6. Be very careful, you will not take the negative sign, okay, into consideration here while calculating the force, into any charge Q, okay, which is to be placed at C, whole divided by separation x into x square, or you can make it here as x into 10 to the power minus 2 whole square. Okay, so we have not made here whole square, so let me put here whole square, because the formula for force is k q1 q2 by r square. This is our equation 2. Okay, now as per the question, the resultant force must be 0, and if the resultant force is 0, this force on C due to A must be equal to force on C due to B. So let's equate both the equations. So from 1 and 2, we can write 9 into 10 to the power 9 into 8 into 10 to the power minus 6 into Q whole divided by, we have 20 into 20 plus x, 20 plus x and in whole power 2, and 10 to the power minus 4 I am taking here outside. From where I got this 10 to the power minus 4? 10 to the power minus 2 whole square is 10 to the power minus 4, and let's put it equal to 9 into 10 to the power 9 into 2 into 10 to the power minus 6 into Q whole divided by x square into 10 to the power minus 4. Correct? Now let's cancel out the common terms. So 9 into 10 to the power 9 cancels out both the sides, 10 to the power minus 6 cancels out both the sides, Q cancels out both the sides, and 10 to the power minus 4 cancels out both the sides. What we left with here is 8 upon 20 plus x whole square, correct, is equals to 2 upon x square. Let's cross multiply here. So this will be 8 upon 2 must be equal to 20 plus x whole square upon x square. I hope this is clear. So 8 by 2 is 4. So 4 is equals to
20 plus x upon x, we have combined both of them, whole square, and taking square on the left hand side, it will be 2, which is equals to root, because square if you take it on the left hand side, it will become root. So root of 4 is 2, equals to 20 plus x whole divided by x. Let's now cross multiply. So this will be 2x is equals to 20 plus x, and taking x on the left hand side, it will become 2x minus x is equals to 20. And 2x minus x is how much? It is x. So x is equals to 20 centimeter. So our correct answer here is 20 centimeter for question number 6th. Let's move to question number 7 now. Problem number 7 says there are 3 equal charges, each of magnitude 2 into 10 to the power minus 6 are placed at the 3 corners of a right angle triangle. So let's draw here a triangle. So here our triangle is, let's say I am making a triangle over here. Okay. So this is our triangle over here, right angle triangle. Okay. And each corner has a charge. How much charge? 2 into 10 to the power minus 6. Correct. And here also 2 into 10 to the power minus 6, and here also 2 into 10 to the power minus 6. Correct. Okay. Now what are the sides? Let's assume this is 3 centimeter. Okay. And another one, this must be 4, and this is 5 centimeter. Correct. Find the force on the charge at the right angled corner. So you have to find the force acting at, let me name it here as A, B, C. You have to find the force on B. So our basic objective here is force on B, on charge at B. How do we find force? Let's see. So first of all, if a charge is placed at this corner at B, the force experienced by it will be repulsive due to charge at A. Why repulsive? Both are same in magnitude, right? So polarity also same. So repulsive will be along the line joining the 2 charges. So force on B due to A. Force on B due to C will be along this direction. Force on B due to C. Correct? Along the line joining. What is the angle between force on FBA and FBC? The angle between them must be 90 degree because vertically opposite angles, right? So here theta is 90 degree. You should remember that cos 90 will be equal to 0. Correct? And if cos 90 is 0 and we use the resultant formula, what is our resultant formula? R will be equal to root under A square plus B square plus 2AB cos of theta. And if cos theta is 90, theta is 90, cos 90 is 0. So this will be root under A square plus B square. That will be your resultant, right? So net force, we will make use of this. Net force on B will be equal to root under force on B due to A square plus force on B due to C square. Correct? So let's figure out what are the values of FBA and FBC. So FBA, force on B due to A will be K. What is Q1? Q1 is 2 into 10 to the power minus 6. What is Q2? 2 into 10 to the power minus 6. And what's the separation between them? 3 centimeters. So 3 centimeters square is 9 centimeters. So 10 to the power minus 4. I converted centimeter square into meter square, 10 to the power minus 4. I hope this is clear. Now let's find the force F on B due to C. That will be K into first charge 2 into 10 to the power minus 6 into 2 into 10 to the power minus 6 whole divided by, what's the separation? 4 centimeter. 4 4s are 16 into 10 to the power minus 4. I hope this is clear. Okay. This is our force on B due to C. Let's substitute in the resultant formula to figure out our net force. So our net force will be here FB, that will be equals to root under FBA square. So let's substitute here K plus 2 2s are 4 into 10 to the power minus 12 whole divided by 9 into 10 to the power minus 4 whole square plus FBC, which is K into 4 into 10 to the power minus 12 whole divided by 16 into 10 to the power minus 4 whole square. Now what we will do? We will take common out. So common out here will be root under k square, k square is common, into 4 into, here it is into, not plus, here it is 4 into 10 to the power minus 12, okay, whole square, this is also common, and 10 to the power minus 4 is all square common, correct? I hope this is clear. So this will give you here into, we left with 1 by 9 square, which is 81 here, and here we left with 1 by 16 square, which is 256. I hope this is clear after taking common out. And when you take this out, it will be k, which is coming out of the root, into 4 into 10 to the power minus 12 coming out of the root, and here 10 to the power minus 4 coming out of the root, and inside the root we left with 1 by 81 plus 1 by 256. Let's cross multiply. Okay, so on cross multiplying we will get here 256 plus 81 whole divided by 81 into 256, which is nothing but 20736. Clear? Now putting the values here, okay, the value of k will be 9 into 10 to the power 9 into 4 and 10 to the power minus 12 and plus 4 minus 8, and root of 256 plus 81 is root 337, and root 337 is 18.35, or let's make it 36 whole divided by 20736. So root of 20736 is nothing but 144. So let's substitute here 144. Now further simplification will give us the final force on B must be equals to, let me directly solve this. So 9 into 4 is 36, 36 into 18.36, that is 660 whole divided by 144, that's 4.59 into 10 to the power 1, or we can make it as 45.9 newtons. This is our net force on B. Let's move to our next question. Question number 8. It says, two small iron particles, each of mass 280 milligrams, are placed at a distance 10 centimeter apart. If 0.01% of the electrons of one particle are transferred to the other, find the electric force between them. Atomic weight of the iron is this much, 56 grams per mole, and there are 26 electrons in each atom of iron. Clear? So here we will require some basic concepts of chemistry, like moles, how to calculate number of moles and all. Okay. First of all, let's go into finding the number of electron in each 280 milligram of iron. Okay. So first of all, to find or calculate the electrons, this is a particular method. We will find moles. So what is the given mass? Given mass here is 280 milligrams, 280 milligrams. And what is the molecular mass of iron? Molecular mass is 56 grams. So be very careful, you have to convert here. So molecular mass of iron will be given here 56 grams per mole. Now if this is 56 grams per mole, what we have to do? We have to find number of moles here, right? So number of moles is given mass upon molecular mass. So it is 280 divided in milligrams. So 10 to the power minus 3 whole divided by 56. Correct? So this will be your total number of moles. Now each molecule has how many number of molecules? 6.022 into 10 to the power 23, right? So number of molecules of iron present in these number of moles will be 6.022 into 10 to the power 23 multiplied with number of moles here. Correct? Okay, great. Now if this is your number of molecules, each molecule contains how many electrons? 26 as per the question. So what will be the total number of electrons? Number of electrons will be 26 multiplied with these number of molecules. So 6.022 into 10 to the power 23 whole multiplied with 280 upon 56 into 10 to the power minus 3. Correct? These are the number of electrons. So let's simplify it. Okay. So simplifying it will be 56 and 280. Let's cancel out this and see how much we get. This will give us 5, and 5 into 26 if I do 130 into let's multiply 6.022, or let's just make a rough approximation. It will be 780 into 10 to the power 23 minus 3 will be our 10 to power 20. Correct? These are the number of electrons. Now the question is saying how much out of these electrons? 0.01% of the electrons, okay, are transferred. So let's find how much is 0.01%. So 0.01% of electrons means 0.01 into 100 upon 100 into 780 into 10 to the power 20. Correct? These two zeros and 10 to the power 20, I am just reducing this, okay, and making it here as 10 to the power 18. Correct? And 780 into 0.01, that will give us 7.8. So 7.8 into 10 to the power 18 electrons are transferred. Not the charge. Be very careful. This is electrons and not charges. So how will you calculate charge? We know the basic formula, Q equals to NE. Okay. So let me write here. This is our number of electrons which are transferred. These are electrons present in those number of moles or molecules. These are the electrons which are transferred if you read the question carefully. So this will give you Q equal to N. N is 7.8 into 10 raised to 18. And what is the charge on one particular electron? 1.6 into 10 raised to minus 19. So when you multiply both, you will get the total charge. And let's see what is the product giving us. 7.8 into 1.6, that will be 12.48 into 10 to the power minus 1. Correct? This is our total charge Q. So we can remake it here as 1.248 into 10 to the power, or 10 to the power will go. So this is our total charge which is transferred from each atom. Let's read the question once more. Two small iron particles, each of mass this much, are placed at a distance 10 centimeter. If these number of % of electrons from one particle is transferred to the other, then you have to find the force between them. So each particle has a charge of 1.248. So let's find the force. So force will be K Q1 Q2 whole divided by R square. What is R? 10 centimeters. So 10 into 10 to the power minus 2 whole square. 10 to the power minus 2 because it's given in centimeter. Let's simplify it. So first of all, our let's multiply 9 into 1.248 into 1.248. So this will be 14.01, okay, 14.01 or 02, okay, we can make it, into 10 to the power 9 whole divided by, this will become 10 to the power minus 1 whole square, right? 10 into 10 to the power minus 2 is 10 to the power minus 1 whole square, which is nothing but 10 to the power minus 2, and 10 to the power minus 2 goes up and it will be 14, approximately I am writing 14 into 10 to the power 9 to 11, correct? So this will be our net force between these two. This was question number 8. Okay, so question 9. It says, a charge Q is to be divided into two objects. What should be the values of the charges on the object so that the force between the object is maximum? Now for this particular problem, we will require a basic concept of application of derivative from maths, right? And if you are a bio student, you have to just remember two things, okay? The first thing is, if some quantity is maximum or minimum, its first derivative, first differentiation is equals to 0, okay? If it is maximum, then the second derivative will be negative, and if it is minimum, then the second derivative will be positive. Only these things you have to remember, but we will not go into second derivative in this particular problem. We will just focus on the first derivative, okay? And the first derivative will be 0, as I said, even if it is maximum or minimum, right? Okay. Depth of this concept, you will learn it in maths. And if you are in bio, don't worry, you have to just remember this, okay? So here the question says a charge Q is to be distributed between two objects. So let's say this is the first object, I gave it a charge small q. Then how much charge I will be able to give the second object? Q minus Q. And if they are separated by a distance d, then the force acting between the two will be K Q1 Q2 whole divided by d square, right? Now they are saying force is maximum. If force is maximum, then the derivative of this force will be 0. But derivative with respect to what? Now be very careful here, you are taking charges. You are splitting charges. So with respect to charge, you have to differentiate. Correct? So let's differentiate with respect to the charge which we have given to either object dq. So this will be equals to, now k and d square are common out. Let's take it out of the derivative, and derivative d by dq of this quantity q into q. So let's make it simple, q minus q square. Again I am repeating, small q you are differentiating, so capital Q will be treated as constant. It will have to be a constant because it's a given quantity. You can't vary it, okay, before you start the experiment. So k by d square, and derivative here will give you q, and there you will get it 2q. Correct? I hope this is clear. Now df by dq, as I said, it must be 0, so this is 0, equals to k by d square, q minus 2q. Now if I take this k by d square on the left hand side, it will become 0, okay, and that 0 must be equals to q into q minus 2q here, you have to, correct. Now taking this 2q on the left hand side, 2q must be equals to q, and if I divide this, it will become how much? Q is equals to q by 2. So each must be getting a charge of q by 2 to get our force maximum. Great. Let's move to our next question. Okay, question 10 says, two particles each having a mass of 5 gram and a charge this much, 1 into 10 to the power minus 7. So let's write here, each particle has a mass of 5 grams. I am converting here only so that later we will not forget it. And the charge Q is 1 into 10 to the power minus 7 coulomb, stays in limiting equilibrium on a horizontal table, okay, with a separation of 10 centimeters, so 10 into 10 to the power minus 2 meters between them. The coefficient of friction between each particle and the table is the same, okay. Coefficient of friction between the table and the each particle is same. Find the value of coefficient of friction. If you remember, coefficient of friction from 11th standard is mu. Okay, so let me explain you the situation. Situation is, let's say this is a table, horizontal table, okay, and on this table I am placing two charges. Let's say this is charged object 1, this is charged object B, each having the same charges and same masses, okay. M is this given and Q here it's given, okay. And if the charges are same, what they will do, attract or repel? Obviously they will repel each other, but if they are repelling, they will be thrown apart, but they are not going anywhere because there is a limiting equilibrium. Equilibrium means the force, the electrostatic force must be equal to the frictional force, and if it happens, then they will be in equilibrium. They will not go anywhere. And the question is saying that the friction offered by the surface of this table and this charged object both has the same value, coefficient of friction mu. Okay, so one thing is clear, our electrostatic force Fe is equals to the frictional force, right? So what is the electrostatic force between the both of the objects, okay, the charged objects? K, which is 9 into 10 to the power 9, Q1 is 1 into 10 to the power minus 7, Q2 1 into 10 to the power minus 7, and what's the separation? 10 into 10 to the power minus 2, so let's make it 10 into 10 to the power minus 2 whole square. Now what's the frictional force? If you recall class 11, frictional force offered by this table, horizontal plane, is nothing but our mu into R. Let me write here separately, F equals to mu R. Sir, what is R? Normal reaction. If it is a horizontal table, R is nothing but mg, the weight, okay. Reaction force, if weight is downward, reaction force is upward, so R is nothing but mg. So let's substitute here value. Mu we are looking for, okay. M, mass of the each object, 5 into 10 to the power minus 3, and acceleration due to gravity, let's make it 9.8. Okay. In case if it is not given, you have to take it 9.8. Clear? So let's simplify on the left hand side first. 9 into 1 into 1, 9, and 10 to the power, this is 9, and minus 14, 9 minus 14, how much? You will get 5, okay, minus 5, Okay, so this is minus 5, and whole divided by 10 to the power 1 minus 1 whole square minus 2 is equals to mu into, let's multiply 5 into 9.8, that will give us 49 into 10 to the power minus 3, correct? And this we will simplify further as 9 into 10 to the power minus 3 whole divided by 49 into 10 to the power minus 3, and that is equals to the mu. Mu is coefficient of friction. So 10 to the power minus 3 cancels with this, and 9 divided by 49, that will give us 0.18. Okay, that's our coefficient of friction offered between the surfaces of the table and the charged objects.